Okay, this video is to calculate the efficiency of a Carnot cycle, right? So a Carnot engine, remember, is a reversible engine that runs the same forward and reverse. And that means that all the processes need to be either isothermal or adiabatic. And so we've got here an isothermal expansion at some temperature that we call TH. Then next we've got an adiabatic expansion, so there's no heat transfer during that process. We've got another isothermal process. This one's a compression at TC. And then finally we have an adiabatic compression to bring us back to where we started. All right. So our strategy is going to be to use these cycles to calculate QC and QH, the heat in during at the hotter process and the heat out at the cooler process, because we know that the efficiency is work over QH, which is also 1 minus QC over QH. Okay. So remember, at the adiabatic stages, there's no change in heat, and in the isothermal stages, the delta E internal is 0. There's no change in internal energy since there's no change in temperature. Okay. So let's talk about this isothermal the two isothermal processes, because we know that there's no change in heat during the adiabatic processes. So that will tell us the total amount of heat gained and lost. Okay. All right. So because the internal energy, change in internal energy is 0, that means that the change in heat plus the work done on the gas is 0, which means that the change in heat is equal to the work done by the gas. Okay, so we're going to first do this for this green process, the isothermal expansion at the hotter temperature. Again, that's this one here. Right? Okay, so for this process, the work done by the gas, which is equal to that Q that we want, is the integral from V1 to V2 P dV, right? And we can't just do this integral easily because the pressure is a function of the volume, but we can use the ideal gas law to say that PV equals nRT. Solve for P, so that's nRT over V. And so the heat input in this process, then, if we plug this in here, is the integral from V1 to V2 in RT over V dV. Now it's isothermal, right? So that temperature is a constant, and N and R are constants, so we can pull all of that out. So this is nRT. It's an isothermal process at TH, so we'll plug in for that TH there. And then it's an integral from V1 to V2 dV over V, which is equal to nRT H log V2 over V1. Okay. Now, we could do this exact same process for the isothermal compression, which occurs at TC. So that means that QC is equal to nRTC log V3 over V4 by the very same reasoning, right? And so then we want the efficiency, so we want to find QC over QH. So that's 1 minus nRTC log V3 over V4 over nRT TH log V2 over V1. Right, so those NRs cancel out, okay? And we have 1 minus TC over TH log V3 over V4 log V2 over V1. Okay, and then now here's where we're going to use our condition for an adiabatic process. So if I'm going to scroll back up to our diagram, right? So in our diagram, we have these two adiabatic processes, one going from TH to TC, from 2 to 3, and then the other going from TC to TH, 4 to 1, okay? And so we're going to use adiabatic process, the first adiabatic process, and we're going to use our condition that TV to the gamma minus 1 is constant for an adiabatic process. And we're doing this to try to simplify this expression for the efficiency that we've already gotten, to make it, see if we can find something that depends only on the two temperatures and not on these volumes, okay? All right, so for our first adiabatic process that goes from point 2 to point 3, that happens at point 2, we're at TH, right? And then at point 3, we're at TC. All right, so that gives us something that looks like this, right? And then for our other adiabatic process, going from 3 to 4, we're at from 4 to 1, we're at V4 when we're at TC, and then we're at V1 when we're at TH, okay? So we can divide these two equations by each other, and actually it would have been better for me to write this the other way around, so let me do that. So I'm just going to switch which side my things are on. All right, and then I'm going to divide the top equation by the bottom equation, which means my THs are going to cancel and my TCs are going to cancel, and I've got V2 over V1 to the gamma minus 1 equals V3 over V4 to the gamma minus 1, okay? And that, of course, means that it's also true that V2 over V1 is V3 over V4, okay? And now I'm going to plug this expression in up here, okay? And that means those log terms can cancel because they're equal to each other. This log V3 over V4 over log V2 over V1, or theirs are equal since V2 over V1 equals V3 over V4. And so then that leaves us finally with our efficiency is just 1 minus TC over TH. So we have this really nice, simple expression in the end for the efficiency of the Carnot engine.